So now that we've talked about the characteristics of acids and bases, how to name them, and then the difference between strong and weak acids and bases, we're now going to talk about pH and several of the equations that go into calculating pH. So I would have your calculator ready for this one as we go through it. The first thing we need to talk about is in pure water, what's going on with hydrogen ions and hydroxide ions. Remember this first, that we were talking about the ionization of water, the auto-ionization of water, that every once in a while a hydrogen can hop off of one water molecule and attach to another, giving you a hydronium and a hydroxide ion. And when that happens, it happens in a 1-to-1 ratio. But I told you it happened about 1 in every 10 million water molecules or something like that. Well, if we look at what that means in terms of concentration, okay, in pure water, the concentration of these two things is equal because it happens in a 1-to-1 ratio. And it is 1 times 10 to the negative 7th molar. Okay, it's a very small number. That's, a decimal and then 6 zeros and then a 1. Okay, that's very, very dilute. So drinking pure water, you're not going to magically, end up getting, too much acid or too much base. It's just not going to happen. Which means that if you take these two things and multiply them together, 1 times 10 to the negative 7th times 1 times 10 to the negative 7th, you'll get 1 times 10 to the negative 14th. And this is the first equation that we're going to need today, okay? And this is called the ion product constant of water. Ions because, well, these are ions. Product because we're multiplying. Constant because this value is always going to be 1 times 10 to the negative 14th. And this is where this gets really helpful, is that let's say the hydrogen ion concentration goes up. Well, then the hydroxide concentration must go down to maintain this value. It always has to equal 1 times 10 to the negative 14th when multiplied together. Okay? So this is a very useful equation. It's true in pure water, but it'll also be true in any acid or base, that the hydrogen ion concentration must, multiplied times the hydroxide concentration, must equal 1 times 10 to the negative 14th. Well, because hydrogen ion concentrations and hydroxide ion concentrations are usually very small, chemists have adopted an easier way to write and record these values, and that is pH and pOH. So this is going to refer to acids, and this one will be referring to bases, right? Power of hydrogen and power of hydroxide, okay? pH is equal to the negative log of the hydrogen ion concentration, okay? It's not times the hydrogen ion concentration, it's negative log of the hydrogen ion concentration, all right? So this has to do with exponents. All right, so here's what I want you to do, right, with your calculator. Make sure that you get this and get it correct. The hydrogen ion concentration in pure water is 1 times 10 to the negative 7th molar. What's the pH of pure water, right? If you know anything about the pH scale, it goes from 0 to 14, where 7 is neutral. Well, if you type into your calculator negative log and then 1 times 10 to the negative 7th, you should get a pH of 7, which would tell you that it's neutral, okay? The pH scale is based on powers of 10, so the distance between numbers isn't, truly 1 apart, okay? So for instance, a pH with 3.0 on the scale is 10 times more acidic than a pH of 4, okay? 0 is the, right, the more and more acidic it is as it goes towards 0. But if let's say a pH of 2.0 compared to 4.0, that's not 20 times more concentrated, it's 100 times more concentrated. If I had a pH of 1.0 compared to 4.0, okay, that would be 1,000 times more concentrated. So you can see it has to do with powers of 10 as far as determining how much more concentrated something is. So 0 to 7, acidic, 7 is neutral, 7 to 14 will be basic on the pH scale. Okay, so much like pH, we can also have pOH, which is for hydroxide ions. And pOH is just negative log of the hydroxide ion concentration. So it looks very similar, plugs into the calculator in a very similar way. And since we had the hydrogen ion times the hydroxide ion concentration equaling 1 times 10 to the negative 14th, you can also have pH plus pOH should equal 14. So equation number 3 is pOH equals negative log of the hydroxide concentration, and equation 4 is pH plus pOH equals 14. Okay? We'll come back to this one later. We'll go ahead and skip ahead, but household ammonia is a cleaner. It's got a pH of 11.6, so it is basic. You can kind of see some examples over here of where things are on the pH scale. So this would be very acidic, neutral, and very basic. Here's just a nice scale laying it all out. A pH of 0 has a hydrogen ion concentration of 1 molar. Okay, a pH of 1 has a hydrogen ion concentration of 1 times 10 to the negative first molar. And if we look down here, right, POH is at this point 14, and the hydroxide concentration would be 1 times 10 to the negative 14th. And so all those equations, you can follow the numbers along the top or along the bottom. All those equations that we learned previously are going to hold true here. Okay, but this is what the scale looks like. All right, pause for a moment and put this into your notes. Okay, this is called the pH square, and it's taken all of the equations that you just saw a few moments ago and conveniently put them into a very simple how to solve for whatever it is you need to solve for. So take a moment and do that, and we'll check back in here in just a sec. Okay, so like I said, this box here, it's called the pH square. It's very convenient. It tells you how to move from one particular thing in the pH equations to another without having to do a whole lot of thinking. Just for our reminder here, when you see a hydrogen ion, it's the same thing as a hydronium ion. So if you see a hydrogen ion concentration, we will treat that the same as a hydronium ion concentration, okay? So this would be the concentration of, say, hydronium. If you wanted to go to pH, you would take the negative log of that number. If you then wanted to go to POH, you would do 14 minus this number. If you want to go from POH to hydroxide concentration, it would be 10 to the negative POH, okay, is how you undo a logarithm. And to go from hydroxide concentration back to the hydronium concentration, it's 1 times 10 to the negative 14th divided by the hydroxide concentration, okay? And you could start any of these corners and move around just following and doing whatever the arrow tells you to do. The most common things you need to watch out for, oftentimes guys will write this as 10 minus pH when you're going from pH to hydrogen ion concentration or hydronium concentration. That's 10 to the negative pH. Okay, down here at the bottom, going from POH to hydroxide concentration, it's 10 to the negative POH. So just be careful with that. But this is going to be really useful when you are solving pH problems here in a few moments. I will make sure to mention this in case I haven't yet. Make sure that you remember these are concentrations, right? And so we can actually kind of get into the square at these points. But remember, this is molarity, okay? It's not moles, it's not grams, okay? It is a concentration. That's what goes into these boxes, all right? So oftentimes we'll have to start outside of the square and then work our way into the square, and we're usually starting either here if it's an acid or here if it's a base and then working our way around. Okay, so oftentimes we start outside of the square. This is for acids, right? If you're starting with an acid, you're going to start there, and this is for a base. And remember, it is for concentration. Okay, so here's a sample problem. 2.00 grams of sodium hydroxide is put into 400 milliliters of solution. What is the pH of the solution? Okay, so what we need to do before we do anything else, and in order to use the square, which we talked about, is that you need to get from grams and volume into a molarity. So let's go ahead and do that first. Okay, to find moles, that's grams divided by molar mass. So that's going to be 2.00 grams divided by 40.00 grams per mole. We will get three significant figures with that. Let me grab a calculator here. 2 divided by 40. So yes, this is 0.0500 moles of NaOH. Okay. And then as far as concentration goes, well, this is a base, right? It's got a hydroxide in it. So we're going to call this the concentration of hydroxide since this is a base. And when it comes apart 100%. So it should be the same thing as the concentration of sodium hydroxide because it comes apart completely. Well, that's moles divided by, right, volume. Well, the moles here are 0.0500 moles. The volume needs to be in liters. So we're going to take this 400 milliliters and turn it into liters. That's 0.400 liters. Make sure the decimal's legible. Okay. And so what we have from that is the concentration is 0.125 molar. From there, I can go into the pH square because I have the hydroxide ion concentration. I can start in that bottom left corner, right? I'm going to kind of sketch this out down here. Okay, we have our square. There we go. pH is in the opposite corner, right? We've got POH in the bottom right corner. So just kind of seeing how this all works, where do we go from here? What is the pH of the solution? So now I have this value, okay? And I'm not going to write in all the equations here. You can look on the previous slide or your notes for that. We're starting here. We need to go to pH. We can go either way. We can go up and then to the right, or we can go to the right and then up. Either way, you'll get the same number. I think the easier way mathematically on a calculator is going to be to go right and then to go up. So let's do that. So to go from hydroxide concentration to POH, well, POH equals negative log of the hydroxide ion concentration. Okay, and so if we take the log of 0.125 and take the negative of that, that is going to be 0.903. Another thing to note, and I haven't mentioned this yet, pH and POH are unitless. There are no units with it. It's just a value. So we have POH, and then to go from POH to pH, it's 14 minus POH, so pH equals 14 minus POH. Right? I'm just pulling those equations from the previous page. 14 minus 0.903, okay? 14 minus 0.903 is going to be, what, 13.097, okay? And that's the answer. It's very basic, right? 14 is kind of the extreme of our scale, and this is 13.97, so 097. So this is pretty darn basic. Okay, so I want you to try this one. What is the pH of a solution if 50.0 grams of HCl are dissolved in 10.0 liters of water? Now be careful this time. You've got an acid. So when you go into the pH square, right, you are going in at the corner with the hydronium ion because this is an acid. So give this one a try, and we'll solve it for you here in just a moment. Let's see how you do. Okay, so here's the solution. First, got to get get moles. So grams divided by molar mass, 50.0 divided by 36.46 equals 1.37 moles of HCl. Now it's an acid, so when you're solving for concentration this time, it's H3O plus and not the hydroxide ion. And so that's going to give us 1.37 moles divided by 10.0 liters. That's 0.137 molar. This time you're starting in the top left, okay, of the pH square, right? And you're going to the top right. So there's only one calculation to go from hydrogen ion concentration to pH, right? Or just hydronium concentration to pH. That's negative log of that value. So negative log of 0.137 is 0.863. Hopefully you did well on that.